Welcome to this engineering deep dive. Today, we're going inside a modern LCD projector to see how it's built. From the light source to the projection lens, every part plays a critical role in creating the image you see on your wall. Let's strip away the casing and examine the sophisticated engineering hidden inside this compact device. We'll follow the light through 8 key stages, explaining the physics and mechanics of each component. It all starts here with the core of the system, the high-intensity light source. In a modern projector, we typically use a powerful 100-watt COB-LED. It's incredibly bright, but it generates immense heat. To prevent damage, we mount it directly to this large heatsink, which draws thermal energy away from the semiconductor. A dedicated fan ensures a constant flow of air, keeping the light source at a stable operating temperature. Once powered, the LED produces the pure white light that will eventually form our projected image. However, raw light scatters in all directions. To make it useful, we need to focus it forward. Without a reflector, over half of our light energy would be lost, hitting the internal walls of the projector housing. We place the LED at the focal point of this metallic bowl. Its job is to capture every stray ray of light. The parabolic shape reflects the light into a unified, forward-moving beam, dramatically increasing our light efficiency. Next, we have to deal with the invisible energy that can destroy our components: heat and ultraviolet radiation. The light beam carries significant infrared energy. If this reaches the LCD panel, it will cause thermal degradation and pixel failure. This specialized filter glass blocks the heat while allowing visible light to pass through untouched, acting as a thermal shield. By stripping away the infrared and UV rays, we ensure the longevity and color accuracy of our projection system. Even with a reflector, the light is still slightly divergent. We need it to be perfectly parallel and organized. A Fresnel lens is a masterpiece of optical engineering, using concentric grooves to bend light with minimal weight and thickness. As the rays pass through, the lens straightens them into a uniform field. This is critical for the next stage, the LCD panel. This is the heart of the projector. The LCD panel is where the digital world meets the physical path of light. Unlike a TV, we don't look at this screen directly. Instead, we use it as a sophisticated light valve. Each of the millions of pixels acts like a tiny shutter, controlling exactly how much light can pass through at any given moment. In dark areas of the image, the liquid crystals twist to block the light. In bright areas, they untwist to let it pass freely. But the LCD needs a brain to tell it what to do. That's the job of the HDMI driver board. But the LCD needs a brain to tell it what to do. That's the job of the HDMI driver board. These signals travel through the ribbon cable, updating every single pixel 60 times per second for smooth motion. After the light passes through the LCD, it's carrying our image, but it's still scattered. We need a second Fresnel lens. This lens gathers the image-carrying light and directs it toward the final stage, the projection lens assembly. Without this second lens, the image would lose brightness and clarity at the edges of the final projection. Finally, we reach the projection lens. This is high-end optical glass designed to magnify our small image onto a massive wall. Inside, multiple elements correct for distortion and color bleeding, ensuring the image remains sharp from corner to corner. It's the last gatekeeper of our image, and its quality determines the ultimate sharpness of our home theater experience. By moving the internal glass elements, we can shift the focal point, bringing the pixels into perfect alignment on our screen. Now that we've seen the parts, let's watch the entire journey of light from start to finish. Light is born in the LED, focused by the reflector and purified by the heat filter. It's organized by the first Fresnel, modulated into an image by the LCD, and gathered again for the final stretch. Finally, the projection lens magnifies that light, casting our high-definition image onto the wall in a dark room. Building a projector requires absolute precision. Even a millimeter of misalignment can ruin the final output. We secure the light source first, ensuring it has a solid thermal connection to the external cooling vents. The optical components are then aligned. This ensures that the light path remains perfectly centered through the lenses and the LCD. With all that light and heat in such a small space, we need a high-performance cooling system to keep it all running. Dual fan systems create a push-pull airflow, preventing heat from building up around the delicate liquid crystals. Precision engineering also ensures these fans are as quiet as possible, so the cooling doesn't distract from your movie. And here is the final result. All those components working in perfect harmony to deliver a cinematic experience. With over 800 ANSI lumens and vibrant colors, the engineering effort becomes invisible as the story comes to life. Now you know what's actually happening inside your projector every time you press power. Thanks for joining us for this engineering deep dive. We'll see you in the next training session.